Okay, I'd like to solve the following problem titled Sample Means Example A. This is a direct relationship to the central limit theorem and is really the foundation for a lot of the things that we're going to do with statistics. So it's essentially the reason why we can relate everything back to a normal distribution. So let's go ahead and take a look at an example problem. We have a quality control department. The quality control department employs 5 technicians during the day shift. Listed below is the number of times each technician instructed the production foreman to shut down the manufacturing process last week. So the table is on the next slide, but these are the questions that we are asked to answer. How many different samples of 2 technicians are possible from this population? So we're talking about a combination at that point. List all possible samples of 2 observation in each and compute the means of each sample. Compare the means of the sample means to the population means. So we want to take a look at that and see what we observe. And finally, D, compare the shape of the population distribution with the shape of the distribution of the sample mean. Okay, so let's take a look at the data that was provided. We have in total 5 technicians that they had various shutdowns in the week, and this is going to be the basis of our study. So let's go ahead and open up the starting file for this solution. Okay, so as you can see in this starting file, we have all the questions listed that was in the PowerPoint along with the data table. The first part of this problem, we need to identify how many total combinations there are. So let's go ahead and start documenting this process in Excel. So how many different samples of 2 technicians are possible from this population? So in Excel, if we look at the COM_BIN, and I'll just go ahead and type this here, total combinations. Let's go ahead and look at the formula. We have the parameter number and number chosen. So that's exactly how I'm going to document this above here, that we have a number and we have a number chosen. So let's say number chosen, and we have to think about this a little bit in terms of what do we want in these cells to do the calculation. Okay, as far as the number, there are in fact 5 technicians. We can either type that in, or what I like to do is utilize some of the Excel functions. How about count, and let's say count A, which is going to count everything. So if this table grows in the future, it'll recognize that and give us the total combinations. So chosen, we have 2. We can't really relate that to the table in any way because this was a specific property in the problem itself. So I'm going to go ahead and type a number 2 and finally implement the combination formula. So number is 5. How many do we want to choose? We want to choose 2 out of the 5. So in this case, you have to think about the order, and in this case, order does not matter. So it's a combination. So for example, the pair Taylor and Hurley is the same as the pair of Hurley and Taylor. The position of those names do not matter. So it's a combination. Let's go ahead and format this as we go. Okay, now the second part lists all possible samples of 2 observations each and compute the means of each sample. Let's go ahead and start documenting this, and we're going to need a table. We're going to need the combination number, and that combination number will go to 10. So let's go ahead and fill out the left side of the table and go all the way to 10. And we'll need a couple columns here for our calculations. So I'm going to provide some borders for that. We'll have a column for technician number 1. And I'll just put technician 1 here and technician 2 here. And let's go ahead and format this table the best we can. Um, Technician 1 and 2. So what are we trying to achieve with this Technician 1 and 2? Well, these two columns represent the sample that we want. We want a sample size of 2. So what we really want to do is pair Taylor with the rest of the technicians. So the first pair that we have will be Taylor and Hurley. Now, Hurley is the second technician, and we want to pair Taylor to Hurley, Taylor Smith, Taylor Miller, Taylor Thomas. So let's pull down this reference until we get to Taylor Thomas, which would be here at sample 4. So this is exactly how I would start building this table until we get all the way down at the bottom. The next combination, we're going to pair Hurley up with Smith. And we can bring that down 2 rows because there are 2 people, 2 technicians below Smith. So we go all the way from Hurley Smith, Hurley Miller, and Hurley Thomas. Let's go to the next one. After Hurley, we have Smith. And if we pair Smith up, it's going to be with Miller and Thomas. So we only need to fill down 1. The final combination is going to be Miller, and the last item is Thomas. So we have all of our combinations. Now, we need to know how many shutdowns there were. That's actually what we're taking the sample off of. So we have shutdowns that relate to Technician 1 and shutdowns related to Technician 2. I think the best way to solve this is with an index, so we can look up in that table and pull out the number of shutdowns. So let's make our reference array the number of shutdowns, match the technician number 1, look up technician number 1 in this technician field, match will be 0, comma 1. Okay, so we have this in order, so let's go ahead and hit enter, fill this down, fill it to the right. Double check the last item, we have Thomas, and it looks like our references are the same. So we could have manually entered these numbers, but of course that would take some time. Now we have the mean of the sample. The sample pair is what we're referring to. So let's go ahead and take that average. Average of 4 and 3 is 3.5. Fill this down the rest of the way, and we have all of our samples. Okay, so this is complete now in terms of listing all possible samples of 2 observations and computing the mean. So we have the mean of each sample. Now let's look at C. Compare the mean of the sample means with the population. Okay, so let's go ahead down here and start documenting the solution to part C. We have the mean of the sample means, the population mean, and let's go ahead and write a conclusion about what we observe. Okay, so this is basically the next portion of our problem. The mean of the sample means will be an average of the sampled means. And if you want to call this sample means, that's fine. Let's go ahead and change that. And we'll change this reference to. And now let's look at our population mean. The population mean is going to be the average of our original values in the table. These represent all of our population. We have 5 workers, 5 is the entire population. So we can conclude that these are exactly equal. So we can show more decimal places if you'd like, but they are exactly equal. Okay, the conclusion, of course, is they are equal in value. Let's provide a little format here with a black fill, white text bold, and move on to this last portion of the problem. Compare the shape of the population distribution with the shape of the distribution of the sample mean. Okay, let's go ahead and work on that. Okay, we're going to need some bins. By bins, I mean essentially a range at which we are expecting values to occur. So I have a bin size of 2, 3, 4, 5, and I got that in the wrong column, so let me move this under here. And I'm going to have two calculated fields. One is going to be based on the frequency of the population, and the next one is going to be the frequency of the sample, let's just say. Okay, we can utilize a function in Excel called frequency. It's actually going to be an array formula. So we have the data array, which from the population will be our data here, and we have the array bins, and that is going to be here. Let's use our dollar signs. I'm going to hit enter just to enter the formula, but what we need to do is highlight this entire range, go back to the formula editing bar, and hit Control-Shift-Enter. So we have the values, meaning we have precisely the count, the frequency count of how many 2s were observed, 3s, 4s, and 5s. Okay, we could have done this with a count if too. And this is nice because frequency actually doesn't require the use of discrete values. So in other words, if we had continuous values, it would be a little bit difficult to do a count if because we would need multiple conditions. Here, it's simply counting the number of discrete values appearing in the table. Let's do this as well as for the sample, and I think you'll understand what I'm trying to say here. In the table here, we've got 4, 3, 5, 3, 2. But here I have 3.5, 4.5, 5.5, and so forth. So let's go ahead and utilize the frequency formula again. Data array for the sample, dollar signs, data array for the bin, and use our dollar sign and hit enter. Highlight the area and go ahead and Control-Shift-Enter to enter that array formula. Now what we're seeing is they don't necessarily match, the sample means don't necessarily match our bin, but we're still generating a frequency, which is why I wanted to use that frequency distribution formula. In terms of values from 0 to 2, we don't have any. The lowest value we actually have is 2.5. So how many values of 2.5 do we have? We have 1 here, 2 here. And how many values of 3 do we have? We have 1 here and 1 here. So we have 4 highlighted cells, which is exactly what this 4 represents. Let's go ahead and graph these just to see what we have, because we've been asked to compare the shapes. I'm going to compare the shapes with just a normal bar chart. Let's put this under the table. It's not exactly what I expected. Let's go ahead and move this over 1. And I think it might be a little bit better to create 2 separate graphs. So let's just concentrate on the population. Let's fix the x-axis because we range from 2 to 5, not 1 to 4. Select data, horizontal, pick the bins, hit enter. OK. And I'm going to copy this and paste it here and actually just simply move this over. Okay, so what we have here is a distribution of the population, which arguably is somewhat normal. And then we have the frequency of the sample, which is arguably normal as well. Now, this might not demonstrate exactly what the central limit theorem suggests, but what the central limit does suggest is that if we sample more, we actually will approach a normal distribution.